Hi, I'm Dennis Milford, Senior Director here at USD Unified Storage Division at EMC. And I have some very exciting things to share with you today. New innovation in the mid-range. First, let's take a look at how are we using a mid-range system today. Well, as we're finding out from talking to a lot of customers like you, we are seeing 95% of all our customers deploying a mid-range storage system in a virtualized environment. In other words, these little controllers here, storage systems, have to actually drive a stack of virtual machines, and there's quite a few. Most customers we talk to now have anywhere from 500 to several thousand virtual machines, all driven by one little array. Now that puts a lot of pressure on the array, and also the array sees all the data. Well, the interesting thing about that is we have found out that the data actually can be sorted into two buckets. Let me share with you what we have learned. First, there's the active data, the data that you currently are working on, the data that's currently concluding transactions for you or helping you with your mission. Turns out that that's only 5% of all the data being stored. What about the other 95, you might ask? Well, that's the data we keep around for historical purposes. But could we get rid of that data? And the answer, of course, is no, we can't, because this is data we use for references, it's data we use to go into just in case we have to go back into historical information. So cold data, hot data, all on the same array, but there's a lot more cold than there is hot. And that tends to stay pretty constant across multiple server farms. Now you might ask, well, what have we done historically to serve this kind of a workload? Well, historically we used to have two controllers for high availability, and the controllers were designed for disk drives, sort of where dual controller RAID arrays came from. So while we designed systems for all disk, we then added solid state. That had a couple of benefits. It allowed us to replace a truckload of drives and actually create a smaller footprint and save money in the bargain. But solid state was an afterthought. We looked at that and said, what if we instead did the opposite? We designed a system entirely from the ground up for solid state. Where would that lead us? Well, we did that. And we said, listen, we need more firepower in the controllers. We still wanted the dual controller design, but this time we optimized the whole stack for low latency. We created essentially an all-flash array. Now remember what I just said a few minutes ago about the 5% hot and the 95% not? Well, that data actually, if we only stuck with all flash, will sit on flash all the time. There would be nowhere else to store it. We looked at that and said, that's not particularly cost effective, because data that no one is looking at can actually tolerate higher latency. And if you're willing to trade out latency, what you can do is actually lower the cost per gigabyte. Low cost per gigabyte? Well, it just turns out mechanical drives are very good at that, especially when we look at around 4 terabyte per spindle. That is a tremendous amount of capacity, and it's very cost effective. So what we said was, we optimized the array for the 5% that's highly active with low latency, and then the 95% of the data that's sitting dormant, well, maybe we should use disk drives for that. Sounds like a good idea, and it was, but it had an interesting little detail to it. Remember when I talked about the all-flash design? Well, let's go into more detail on how we actually did that. So when you build for all-flash, what you have to have is a tremendous amount of firepower on the CPU side. Here, we use 4 sockets of 16 cores here, 16 cores here, so 8 plus 8 plus 8 plus 8, with each individual socket having 40 lanes of PCIe Gen 3 coming out of it. Now, from an I/O guy's perspective, that's like a dream come true. This is an I/O computer, lots of CPU firepower and lots of I/O capability. And that's an important point, because when we build a storage system from scratch, a clean sheet design for flash, if you will, we have to have a lot of I/O to drive the flash and a lot of I/O to do the other thing, which is connect to all the hosts. So for that purpose, we put in a ton of PCIe switching, and we connect that to 22 individual slots of PCIe Gen 3. These I/O slots are then connected to either the back end or the front end in a balanced fashion. And it turns out that when you look at the storage side, here we go up to 1,500 drive slots in a combination of solid state and mechanical drives with fully automated storage tiering, moving the data dynamically between these two outer points. And the question really then was, well, if this is a nice new I/O powerhouse kind of design, do we have the software to drive this? Well, that's the next piece. And this is where the true innovation came in. Because we looked at Flare, and you may remember Flare from the old Clarion days. We actually carried Flare code forward in the older VNX, and it was fine. It worked great. It actually managed to schedule itself across multiple cores, but it did so statically. Now, doing that in a staggered fashion meant that one core could easily become the bottleneck while the other cores were not doing very much. In other words, it didn't evenly use the cores. The new MCX stack stands for multi-core everything, takes all the stuff that has to be happening in the array, turn it on its side, and spreads it across all available cores. And as we just talked about, we have 32 available cores in the VNX today. 32 cores used evenly gives us tremendous core scalability. And when we compare that to the older designs, we're finding that we can scale further and at lower latency than ever before. And this pushes out the need to involve large complex designs into a multi-core scale out. We actually have core scale out on the system itself. And as you can see, latency between 300 microseconds all the way up to 1 millisecond. And the other systems, older systems, both from our competitors and ourselves, simply were never designed to do that. So what are we talking about here? We're talking about brand new hardware optimized for flash from the ground up, and a software stack that takes advantage of all the available cores. Now, what does that mean to you? Good question. It means you have a system now that can solve for a bunch of different workloads. Thousands of workloads on one storage system, 800,000 input-output operations, millions of transactions supported, and 5,000 or more virtual machines. And if that wasn't enough, the virtualization today is, of course, not just virtual machines, but also virtual desktops. This system does that too. Fundamentally, when you build a very high-powered I/O engine, it helps all the workloads out. Well, it means that we actually, in a little system, can scale a very long way. You don't need any more like football fields of disk drives. You need just the right amount of flash with a flash optimized system with MCX, and the right amount of disk drives for the older, colder data, and that allows you to build a very compact system that ends up saving you a ton of money. Where in the past you had to stripe across lots of disk drives. Today you don't need to do that. Today you just let flash do the job, MCX do the job for you, put fast to work, moving data back and forth, and it's all embedded in the brand new VNX system from EMC. Thank you so much for watching. It's been an absolute pleasure spending these few minutes with you.